Adrian will tell us a little bit about DMR. Who one uses DMR? Only a few people, okay. DMR is one of the modulation developments in UHF transceivers, and he will tell us a little bit of his transceiver in software-defined radio as a base station. So,
to show. So hello everybody, thanks for having me here again, this time physically. You might have watched my previous contribution in 2022 regarding the implementation of DMR Tier III or conventional DMR in software-defined radio. This talk will be about some further development on that. Basically, I'm going to introduce the implementation of a DMR Tier III trunk radio base station transceiver in software-defined radio. Thank you. Right, so I'm afraid this talk will focus more on the software side of things, since that is my specialty. So to start with a short introduction of the digital mobile radio trunking. This is an open standard created by the European Telecommunication Standards Institute. And it represents an incremental development of conventional DMR or Tier II DMR with some further building blocks added to it. The air interface of DMR Tier III is basically the same as for Tier II or conventional DMR, so you're probably familiar with the 4-level frequency shift keying in a 12.5 kilohertz channel with 2 time-slot time division multiplex access. Regarding the digital mobile radio trunking, first of all, it's a lower complexity standard compared to other trunked radio standards like Tetra or P25, which are also trunking standards used currently today. That is because this standard is not aimed at mission-critical communications. So it will have some lower prices for the radio terminals, and these terminals are generally easier to procure on the market. Of course, there is lots of existing open source code and some documentation, as well as applications for monitoring, recording, and regarding the interpretation of the DMR Tier III transmissions, generally using software-defined radio receivers. Of course, for this work, we'll use the excellent open source implementation of DMR Tier II in the MMDVM application. Oh, sorry. So what are the trunked radio advantages? Because there is not a lot of information in the amateur radio world about trunked radio. So it brings several new things, such as call capacity increase per a certain radio site. It also optimizes spectrum access, since it will operate in a shared pool of radio resources, which are generally called payload channels, and these resources are or can be shared among many entities, regardless of their usage. It's also a centrally coordinated network access system, kind of like a packet switching in networking, if you're familiar with that terminology. It also has automatic site-to-site handover based on signal characteristics and also on some information which is broadcasted by the trunking site regarding neighbor cells or neighbor channel which are available. Besides that, you have to know that the RF channel, the frequency, the time slot, and the color code are basically irrelevant from the perspective of the user. That is because the access is entirely managed by the trunking controller. Also, in addition to Tier 2, which you're probably already familiar with, it also standardizes short data messages and status messages, which in Tier 2 were not really that well standardized. And it also has additional things like location sharing, packet data calls, call prioritization, transmit interrupt of ongoing voice calls, full duplex calls, basically work like a mobile phone call, and additionally it has IP bearer services, so basically it has IP transport over packet data, as well as can be connected to the public service telephony network or private branch exchanges, which may not be relevant to amateur radio, but it's there in the standard. The management of most of the user terminal functions are pretty much automatic. So, for example, power control or talk channel and frequency, the time slot, that is managed by the trunking controller. So the operation of the radio is basically a lot simpler than for DMR Tier 2. That's from the perspective of the radio user. So a little bit about the principles behind DMR trunking. A trunking site will generally have one or two control channels which are continuously broadcasted, so they're continuous transmissions which are not stopped except for maintenance operations. And the site will also have a number of payload channels. Basically, that's a logical channel pool, which is allocated on demand to the users based on their requests. During normal operations, radios will listen on the control channel when they're idle, and they will receive ongoing call information and also other information which are relevant to the user radio, such as short data messages, which are intended for the radio, or perhaps site configuration messages, which are not technically, they're not visible directly to the user, but the radio will take them under consideration and will adjust the settings. When a user radio wants to place a new call on the system, that request will go on the control channel. So basically, when that request is received, the trunking controller will allocate a new payload channel. And also not just the frequency, but also a time slot automatically based on what is available in the pool of logical channels. Or in case there are no logical channels free, it will choose to reject the call. When a channel grant is received, after the user places the request, the channel grant is received, and then the radio will automatically tune to the frequency of that channel and will begin to transmit, which will be repeated back on the RF. And when the transmission, when it's done, it's over, then the user radio will return to the control channel, and the trunking control will deallocate the resource so that it is made available to new users which are requesting it. Okay, so a short presentation of the DMR Tier III services which are available on a regular DMR Tier III site. You are probably familiar with talk group and private voice call services from Tier 2. But aside from that, we have short data and status messages, like I said before. We have broadcast and emergency call services, which are also available. The trunking controller can prioritize the calls based on the priority. For example, like you have an emergency talk group, say talk group 112. Then the trunking controller can take a call for that priority talk group and drop down existing other calls which are happening on lower priority talk groups. Then you also have things like call diversion, preferential call notification, and full duplex or packet data calls. Other than that, other interesting services are the talk group subscription service, which these services will be requested normally during the registration or will be released during the deregistration procedure. There are also late entry announcements, which basically they are useful when a radio is switched up and an ongoing call is already happening on the system. The radio will be notified by the late entry announcements and will then tune to the correct channel, even though it has missed the start of the conversation. There's also dynamic group number assignment, so that is more like a function which is usable by the dispatcher, let's say. But it's interesting because it can allow a group, say a voice talk group, to be assigned to a radio even without programming the radio. So that's happening at the runtime, and the trunking control will manage that. Additional things are radio presence check, radio power control, and call preemption. For transmit interrupt, and also there are some broadcast services. Things like, so they're basically announcements. The trunking controller will announce used frequencies, neighbor side channels, and any configuration changes which might be happening during the operation. Okay, so to the left here, you can see the architecture of the system and the components which are used to create and to implement this system. Starting from the lower physical level and the connection to the SDR transceiver, there's a QRadioLink application. Then, of course, MMDVM, which implements pretty much the same things as for DMR Tier II, and MMDVM host. But you will have to note that in this case, we have multiple instances, program instances of both MMDVM and MMDVM hosts. So it's not, you may be familiar with the regular repeater or the regular hotspot. In our case, we have multiple program instances running in parallel on the same host, or perhaps on a different host. Get into that a bit later. So, as you can see, the components. I think something went wrong with the display of the slide. So, yeah, the components are basically MMDVM host, QRadioLink, the trunking controller, DMR gateway. I will explain later why DMR gateway has to be used. And the communication between all these programs and processes is done using three different methods. So 0MQ, inter-process communication pipes, which can also be TCP sockets if desirable. And of course, there's a lot of communication happening via UDP data packets over IPv4 or maybe IPv6 between the systems, the components of the system. Also, MMDVM communicates with MMDVM host via a serial interface. In our case, pseudo-TTY, so it's not a regular interface, it's a pseudo-TTY interface. About MMDVM, so I'm sure pretty much everybody here is familiar with MMDVM, written by Dr. Naylor and also other contributors. It implements a lot of digital modes, most notably DMR Tier II, which is why we're using it. This application was modified by Rakesh Peter to run on a Linux system. So instead of running on a microcontroller, as originally it was modified to run on a Linux system, not in a real-time way, and also to communicate via pseudo TTY with the MMDVM host. So not real serial connection. Then I further modified MMDVM to pass samples. So instead of talking directly to the analog and digital converters, to pass samples to and from GNU Radio via 0MQ interprocess communication packets. Also, there have been a number of trunking-related changes. Most notably the DMR idle burst, which occurs when a repeater is idle and sends that periodic message. This burst was replaced with a continuous Aloha burst, which announces the control channel of the system. Of course, that Aloha burst is parameterized from inside MMDVM host, so that required also a slight modification of the serial communication protocol, which controls MMDVM from MMDVM host. Also some minor modifications to MMDVM host to introduce some processing for control signaling blocks, the multi-block format with header continuation, and also some handling for UDT data messages, which are standardized in the Tier 3 standard. Of course, some other modifications were also considered like reverse channel. So reverse channel is basically signaling to the user radio during transmission on the other time slot. So the user radio, due to the TDMA structure, will basically listen to the reverse channel and process any requests. So the components in more detail. QRadioLink, which is one binary, one application written with Qt. It contains GNU Radio flow graphs. So it uses the GNU Radio C++ API with blocks and top blocks and sub flow graphs. And of course, it communicates with the MMDVM, like I said before, via 0MQ packets. In this particular mode, so MMDVM and multi-carrier modes, the graphical user interface is not used, so there is no X server necessary to run on Linux. Because only a CLI interface is needed. And also it presents a command line interface which can be used to control the software-defined radio transceiver at runtime. So some RF parameterization, like setting gain, setting duplex mode, the transmit offset, so that can be configured, so you can change the repeater shift at runtime, and other commands which are useful. The DMR trunking controller, so this is a new application which I've created for this purpose. It's Qt based and can be used with either using the graphical user interface with the X server or using the CLI only, so you can start it from the command line. It's created using some code from MMDVM host, which is modified under the same original license. And it has a display, well, sort of a real-time display, if you ignore the fact that we're running on Linux. So not real-time, but displays calls, register radios, talk groups, and which are subscribed by radios, and will also handle all requests by the user radios. It also has a function of routing an ongoing call towards the correct radio frequency channel, and also towards the correct DMR gateway, correct DMR network. Its limitations are basically it supports maximum 14 logical channels. That would be 7 carriers times 2 time slots. And therefore, it supports a maximum of 13 simultaneous voice calls, plus, of course, the control channel. It also supports some other operations which are available to the administrator of the site. DMR gateway is used because we have sort of have a problem. Most major DMR networks, they think a repeater can only have 2 time slots. So that is causing some issues because when there are 2 incoming calls on the same time slot, the reflector software will block one of the calls on their side. For us, that is not good because we can support, like I said, 13 simultaneous voice calls at the same time. So as a solution, we use DMR gateway to connect, basically present to the DMR reflector, present our repeater as many repeaters, which are basically, it's not exactly what's happening, but that's the way the network will see our repeater. Also, DMR gateway is slightly modified to allow 2 calls on the same time slot. Notably, for incoming calls from the network side towards the RF side, there is no need to rewrite the time slot because it will be assigned by the trunking controller, so it won't be statically allocated, but instead based on resources. About the software-defined radio hardware, first of all, I would like to say that not all hardware can be used for this purpose because it needs to provide some FPGA-based timestamps in order to do the time slot synchronization, so time division multiplex access requires that. I've tried to use these 2 transceivers mainly, so the Lime Microsystems LimeNET-Micro, also possibly the Lime SDR Mini, and the Ettus USRP. There are several bus variants which all should work as well. And these devices are supported by GNU Radio modules, GNU Radio Lime SDR and GNU Radio UHD. Also, it's possible that the Adam Pluto can also be used for this purpose because it can be modified, so the FPGA can be modified to support time division multiplex access. Okay, so more details about the multi-carrier transceiver which enables this. It employs 2 different access schemes, so time division multiplex access for a DMR channel and frequency division multiplex access, which are a number of RF carriers which are transmitted and received at the same time. The lower physical level is implemented in GNU Radio C++ flow graphs. Like I said, supports maximum 7 RF carriers and minimum of 2 carriers. The upper physical level and the MAC and call control is not done inside GNU Radio. It's implemented by MMDVM. The techniques are used here, multi-threading technique used inside GNU Radio. GNU Radio runs multiple threads, so 1 thread per block. And also there's multiprocessing, which is happening between all these MMDVM instances and the other programs included in the system. Basically, each MMDVM instance can be configured for any of the modes supported by it, except for baseband carrier number 0, so that needs to be DMR because of the timing synchronization issues. Here you can see a schematic which is showing that multiple access schemes like TDMA and FDMA can coexist. And the time slots are aligned in time, including frequency division multiplex access transmissions are also aligned in time with the TDMA transmissions. Okay, so about the receiver. Receiver consists of, first of all, GNU Radio flow graphs. Thankfully, all the modes implemented within MMDVM utilize some form of frequency shift keying. And they also use the same baseband sample rate, 24,000 samples per second, which is very convenient from a digital processing side. The flow graph here performs a frequency shift to baseband of samples coming from the GNU Radio source, so basically from the device. Then it will also perform some resampling and, of course, filtering. Then finally, frequency demodulation so that we get to actual symbols. Along the way, along with the samples which are circulating through this parallel flow graph, there are also time tags from the GNU Radio source. These time tags are used to synchronize time slots based on some marks which are synchronized by the burst timing code. Right, so the GNU Radio sync is the most complex block here, which sends the samples together with the metadata like time slot marks and receive signal indications via 0MQ packets and push-pull sockets to each MMDVM instance. The transmitter, this is a bit more complicated than a receiver. The timing is driven by the GNU Radio scheduler. The source will basically request one time slot worth of samples from MMDVM via 0MQ request reply sockets. And then the source will have multiple outputs connected to each branch of the flow graph. With basically the same process repeated in reverse, frequency modulation, resampling, and frequency shift to the carrier position in the frequency raster. If there are no samples for a certain carrier, so for a certain MMDVM instance, because that carrier is idle, those samples will be zeroed out after the frequency modulation, so downstream from it, because we want to avoid a continuous carrier. The burst timing code here, which allocates and tags with the TX time tags, is common with the receiver. So, like I said before, only carrier 0 must have these tags to avoid dropped samples. And the samples are tagged and transmitted into the future. So we need to allow for the latency of the flow graph to allow the samples to be transmitted sometimes like 60 to 80 milliseconds in the future. So this is RF characterization. This is what the waveform looks like, captured on the signal analyzer. You'll note here that all 7 carriers are continuously transmitted for test purposes. The device sample rate is 240 kilosamples per second, and the effectively occupied bandwidth is 168.5 kilohertz, with a maximum of 7 RF carriers. The channel raster is 25 kilohertz, so each of the carriers is separated from the other one by 25 kilohertz. You'll note that the unwanted emissions in the out-of-band domain, so in the adjacent channel, are a bit high, so they're about 42 to 46 degrees below the carrier power. But then at more than 100 kilohertz, that goes down. So it will be about 50 dB. Some challenges were encountered during the creation of this. First of all, the CPU efficiency for the whole system on small ARM platforms, embedded Linux. It's not that great, so only 4 carriers are possible. Then, of course, the latency. We can't avoid having latency of about 330 to 40 milliseconds. That means coming from the trunking controller to radio and back to the trunking controller. And the latency is caused by multiple IP hops, the 0MQ overhead, communication overhead, multiple buffers, especially GNU Radio has 1 buffer per block, and some limitations in the source block from the GNU Radio thread scheduler. Unfortunately, only 1 type of radio could be tested, and I've noticed that kind of each manufacturer likes to deviate a little bit from the standard, which is a bit problematic. About RF amplification for this particular waveform, because when you double the number of carriers, you will automatically have to reduce the power per carrier with 3 dB. So then if you plot the signal power across time, then you will notice something like a square wave, since there are abrupt transitions when a carrier becomes idle or if it becomes active. Another thing which should be noted is that 4-level frequency shift keying should be theoretically constant envelope, constant amplitude, but in practice the resampling filters do introduce some amplitude variation. And also, like I said before, the noise which is radiated in the out-of-band domain in the radiation to 12.5 kilohertz channel, which are not used, is a little bit higher than desirable. So I hope this work will continue to make the deployment a little bit easier with using some containerized system deployment with Docker, and also implement some other aspects of the standard which haven't been implemented so far. And also, hopefully, the latency could be improved with some better coding, and also the CPU efficiency, which is currently a bit limiting on ARM embedded Linux. Also, if possible, I would also like to support the Adalm Pluto SDR for this, but that requires kind of a lot of work because it's not out of the box. It's not compatible with timestamps. So this pretty much all this work and implementation would not really have been possible without some key people. First of all, Dr. Jonathan Naylor, which is the original author of MMDVM. Also, Marcus Müller from GNU Radio. He's basically the authority on the GNU Radio thread scheduler issues. And also would like to thank Marc Sebera, author of a very nice library, Python library called OKDMRlib, useful for testing the PDUs. Rakesh, who basically started this whole thing by implementing, porting MMDVM to run on native Linux, and also the authors of the applications which I've used to monitor and decode the transmissions. Dennis Shearer from SDR Trunk, and the authors of DSD and DSD FME. And yeah, so if you'd like to see more information, then please go to these links, and there should be some documentation and some aspects.
Okay, thank you very much. We have a little time problem because we are 5 minutes over time
Yeah, sorry, I've tried to compress it as much as possible, but apparently there was too much information to present.
Okay, Christoph, maybe you raise your question afterwards. Yeah. Okay, so thank you very much. Last applause.
Thank you.